Hi guys, this is just a quick video, probably 10 minutes max, to go over the last two problems from the sample exam. So number 9, it said consider the space curve given by r of t is cos t sine t t. That's a helix, the same curve that we saw in the, well, except for a few constants, the same curve as we saw in the computer project. And part A of this problem is just to find the unit tangent vector t. Actually, maybe I should say t of t. Find the vector that's a function of time that represents the unit tangent vector as time evolves. So that one's pretty straightforward because you just take the derivative of this to get the velocity vector, and you want a unit vector that points in the same direction as the velocity vector. So let's just do that. V of t, which is r of t's derivative. That's pretty easy. Cos t goes to minus sine t. Sine t goes to cos t. And t, it's by itself, becomes 1. Let me take derivatives. All right, so now, how long is that vector? The length of this velocity vector we've just found is going to be, well, it's the square root of the sum of the squares in there. The fact that that's negative isn't going to matter because we're squaring, so I'm just going to write sine squared t and cos squared t and 1. And then the Pythagorean identity tells you that cos squared and sine squared is 1, so what we've got here is really just root 2. So we're essentially there. To get the unit tangent vector, just take this velocity vector and divide it by its length. I prefer to write that as multiplying out front by the reciprocal of its length. It's a subtle difference, but it feels better to me. I've got a constant times a vector. And then what is the vector? The same thing we just had for the velocity. Minus sine t, cos t, and 1. All right, so the second part of this problem was to find the unit normal vector. There's two ways to do this. You can get the normal vector as a function of s. And this is actually the definition of the normal vector is dt ds. That is, take the derivative with respect to arc length of the unit tangent vector. But we don't really have an arc length parameterization, and it turns out that the derivatives dt ds and dt dt, when they're at the same, at the arc length position that corresponds to the same t position, but evaluated at corresponding moments, those vectors are parallel. So you can go straight to the normal vector as a function of t by just taking the derivative with respect to t. Well, no, not quite, because that, while it's parallel to t, dt ds, won't be a unit vector. I think I'm lying there a little bit. Yeah, sorry. Both of these need to be divided by the lengths of the vectors. I'm going to write this like that. And this one as well by the length of the vector. Now it's the length of dt dt, though. All right, so that's the thing that you will almost always use to find a normal vector. We've got an expression for the tangent vector, take its derivative, and then scale it so that it becomes a unit length vector. All right, so what is n of t? It's going to be, let me just write it because I no longer have that piece on the board. We'll say take the time derivative of this vector, which we, darn, I just erased it. What was it? Right, that's, sorry, I had to go look that up. It was, we might as well get that constant in there too. It was 1 over root 2 times minus cos, no, so minus sine, cos, and 1. And can I just write this sort of, I don't know, I want to cheat a little bit. I don't want to actually have to write this whole thing again, because what I want is the length of that vector in the bottom of the fraction. So let's just write divided by its length. And we'll know what to do with that in a sec. All right. So take the time derivative of this guy. The constant 1 over root 2 just comes along for the ride. Right, that's the constant multiple rule. And then we take the derivatives of the bits inside of the vector. Minus sine becomes minus cosine. Cosine becomes minus sine. And that 1 becomes a 0. So the length of this vector is 1 over root 2. I can tell that because the vector itself is a unit vector. That's on the unit circle in the xy plane. Okay? So to get n of t, the length just needs to be, well, basically we just need to erase this 1 over root 2. Yeah. I'm going to try to squeeze it in here at the bottom. Then it's equal to minus cos t minus sine t 0. I guess the line above really should have included the dividing by the length part. And what I just did there is accomplishing that, dividing that by the length. Okay, so that's the unit normal vector. There's one more thing it asks about, to find the curvature kappa. And there's multiple approaches to that. Let me just fix this. Find kappa. This would be C now. So I guess the most immediate formula for kappa is this one. Kappa is the time derivative we just took divided by the speed. So it's 1 over the velocity. Sorry, 1 over the speed, 1 over the length of the velocity times the size of the derivative of the tangent vector. And that one is supposed to make physical sense to you. The rate of change that the tangent vector is, the rate at which the tangent vector is changing with respect to time, it tells you how the direction of motion is changing. If that's large, it means you're going around a sharp curve. Right? If it's small, then you're more or less on a line, maybe slightly curved. And the velocity enters, or rather the speed enters into it, because there's sort of, there's, how to put this nicely, this rate of change may seem large if you're on a parameterization that is going through the curve, through the point of interest really quickly. Well, this sort of accounts for that. It accounts for the effects that come just because your parameterization is super fast or super slow. dt could be quite small, even though you're on a very tightly curved thing, if you're going super slow. So, and vice versa. The derivative may seem large on a relatively slight curve if the velocity is gigantic. So anyway, that's a formula for curvature that's probably the most useful. There's another one that we'll look at in a second, but let's do it this way. We actually have these elements. Right? The speed was root 2, so that's 1 over root 2. And dt was, let me recall it, it was 1 over root 2 times negative cos t, negative sine t, and 0. I think I already remarked that this vector's length is exactly the number that's out front, because the part that's inside the vector here is just on the unit circle in the xy plane. Yeah. So this is 1 over root 2 times 1 over root 2. The curvature there is a half, which means the osculating circle's radius is 2, if you want to think about it in terms of radius of curvature instead. It's the reciprocal of the curvature. Okay, and now the last problem we didn't get time for in class was number 10, but honestly, that's almost too easy because it's nothing but taking a bunch of derivatives. So, except for the vector dressing that it's in, it's just do a bunch of derivatives. So number 10 was, and know the terminology, I suppose, too. You were given a space curve. It's e to the t, sine t, and t. That vector is r of t. And what it asked us to do was find velocity, acceleration, and jerk. For the space curve. Okay. So the velocity vector, v of t, that's just the first derivative of the position vector. And so, well, e to the t is its own derivative, right? So we'll have e to the t there. Sine t's derivative is cos t. And t's derivative is 1. We were taking derivatives with respect to time. So there's your velocity vector. Your acceleration vector is well, you could do it as the derivative of the velocity, but I prefer to just say it's the second derivative of the position vector. And, well, okay, but it does mean I'm just going to look at the thing above and take one more derivative on everything. So e to the t is never going to change, is it? But cos t is now going to become minus sine t. And the 1 is going to turn into a 0 at this stage. Now your jerk vector, I think this is probably a little bit of a weird thing to do because it usually reserves j as the vector, the unit vector in the y direction, but I hope you know what I'm talking about right now. In this context of this problem, j for jerk. That's the third derivative of the position vector. So what is that going to be? E to the t, of course. Sine goes to cosine, we got a minus on it, so minus cosine and 0. So that's all that problem asked for. Okay, so I'm going to end this now. I'm going to also be sending out an email with instructions on how to sign up for the oral portion of the exam. I'm going to slot it out a whole bunch of time on Friday from a couple hours before our test to several hours after it as well. And just get people to come into video chats with me on Teams. But that information will come out in an email, so you have it in writing. See you Friday.